Over the past 8 months, the UCAV team designed, tested, and flew a custom-built UAV for the AUVSI competition. After hours of development and flight testing, we are ready to see our design fly at the competition. Austin Wessels, class of 2019, first year on the team. Team captain, hardware assembly and test pilot. Several years experience with UAVs. Primary safety pilot on the flight line. Nick Little, class of 2020, first year on the team. Hardware lead, worked on CAD design and vehicle assembly. Several years experience with UAVs. Safety officer on the flight line. Nick DeGroot, class of 2020, first year on the team. Software lead, worked on imaging system and obstacle avoidance. Several years experience with UAVs. GCS operator on the flight line. David Kroc, class of 2019, first year on the team. CAD modeling, UGV and drop mechanism design. Limited experience with UAVs. Payload drop operator on the flight line. Simon Livingston, class of 2019, first year on the team. Hardware assembly, ground vehicle design, and media lead, with limited UAV experience. UGV operator on the flight line. Evan Barnes, class of 2020, first year on the team. Worked on software with object detection, classification, and localization. Limited UAV experience. GCS operator number 2 on the flight line. David Wenner, class of 2019, first year on the team. Worked on search area and path planning, as well as obstacle avoidance. Limited UAV experience. Visual observer on the flight line. Jason Roll, class of 2019, first year on the team. Worked on search area and path planning, as well as GUI development. Limited UAV experience. Antenna operator on the flight line. The vehicle that the UCAV team is using is an octocopter UAV in the X8 configuration. The 4 arms each have 2 motors mounted coaxially. This platform was designed to have the thrust needed to lift all the required payload at the competition, while also having enough endurance to accomplish all the mission tasks the UCAV team attempts. Our custom-built UAV has a lightweight structural design that separates components into different layers. The arms are made from carbon fiber tubes, while the mounting plates are made from carbon fiber plate. The different layers of components within the airframe allow for rapid removal and replacement of broken or faulty components, while also separating components which might otherwise have caused interference with each other. Thrust is generated on the vehicle by propellers driven by 8 brushless motors. With 2 motors attached to the ends of each arm, there is an inherent failsafe in case of a motor failure. The ground vehicle is a modified RC car fitted with sensors and peripherals necessary to make it run autonomously. It operates using a PIX racer for the driving controller and uses GPS to drive to its intended location. The drop mechanism, utilizing a fishing reel, was designed to be lightweight and reliable. Its simplicity ensures that the payload will be dropped as expected every time. 2 6-cell lithium polymer batteries provide the power for our vehicle. All the electricity is routed through the power distribution system that supplies power to the vehicle's different components. The vehicle utilizes a 5.8 GHz Wi-Fi network to communicate with the ground station and a 2.4 GHz network to communicate with the safety pilot's transmitter. Good communication with the vehicle is important for both safety and reliable telemetry transfer. Both the Wi-Fi link and the safety pilot connection were tested to beyond 1,000 feet per the proof of flight requirements. The vehicle takes images with the Sony a5100 mirrorless camera attached to a 2-axis gimbal. To perform various tasks mid-flight, including image capture, the vehicle has an Odroid XU4 onboard computer installed. Autonomous flight is controlled by a Pixhawk 2.1 flight controller. The Pixhawk also provides support for additional sensors and peripherals such as GPS, a safety switch, and a telemetry link. The Pixhawk runs PX4 Autopilot as the vehicle's firmware. PX4 implements the essential parts of the mission, including autonomous takeoff, autonomous landing, and waypoint navigation. High-level mission flight planning is controlled by a custom software package called FlyMaster, originally developed by the UCAV team for the 2017 AUVSI competition. FlyMaster gives the GCS operator a visual interface for displaying the UAV location, as well as waypoints and obstacles. Manual approval and rejection of targets is done through a Python GUI built for this competition. The GUI allows the GCS operator to manually identify any targets that the autonomous algorithm couldn't identify. The UCAV team plans to attempt flying completely autonomously at the competition and has high confidence in each of the autonomous mission tasks, which include autonomous flight, waypoint capture, and waypoint accuracy. The stationary obstacle avoidance task will be attempted, and we have high confidence that we will complete it. The UCAV team will attempt all the object detection, classification, and localization tasks, including identifying object characteristics, determining object geolocations, submitting actionable objects, and submitting objects autonomously. We have high confidence in characteristics, geolocations, and actionable items. We have medium confidence in autonomy. The airdrop and all of its constituent parts will be attempted. We have medium confidence in the drop accuracy, and low confidence in the drive to location. The UCAV team completed hours of testing during the development process to ensure a high quality and reliable vehicle. Our testing process started with simulations and ground-based testing, then continued through iterative steps until we started running full mission tests. After all the testing completed on our platform, we are confident in its ability to perform at the competition. There were several different kinds of testing that the UCAV team used during the development process. Software-in-the-loop testing was used during the early stages of development to verify the performance of software processes, like obstacle avoidance, search area path planning, and waypoint navigation. Verifying the performance of the autonomous navigation system made the transition to mission testing much smoother. In order to verify the performance of the propulsion used in our platforms, every motor-propeller combination was first tested on a thrust stand. This allowed us to gauge how well the motors performed compared to their specifications, allowing us to predict the more accurate flight time. Indoor flight testing was performed for initial tuning and calibration of our vehicle. Flying indoors allowed us to test in a controlled environment before attempting outdoor flight. The next iteration of testing was manual outdoor flight tests. Several flights were completed to verify that the flying characteristics were as expected and to ensure that the efficiency of the vehicle matched our predictions. Autonomous mission testing followed the manual flights. Fully autonomous missions allow for total system integration testing, making sure that all the vehicle systems work together effectively. As of May 14th, the UCAV team has conducted 23 autonomous flights with the vehicle, and has spent less than 1% of the time during autonomous flights in manual mode. Most of the time spent in manual mode during autonomous flights was during initial autonomous flight verification. Our vehicle had to be tuned manually before it could be operated autonomously. The tuning process involves using manual flight to adjust gains for a cascaded PID loop. An iterative approach is used to change the PID gains until the vehicle's tracking error is minimized with few overshoots. Waypoint testing was first done in a software-in-the-loop environment, where 234 waypoints were hit with an average error of 4.1 feet. Next, testing was taken outdoors during autonomous flight tests. The first tests were done using simple mission planning and Q ground control, an open-source mission planning software. Later tests were completed during full mission testing using our custom mission planning software, Flymaster. Over the course of our testing, 26 waypoints were attempted, and all of them were hit. The average waypoint miss error was 3.95 feet. Like waypoint navigation, obstacle avoidance was first tested in a simulated environment before it was taken outside. The algorithm is designed to never let the UAS cross the flight boundary, important for promoting safety during the competition, especially with the rule changes to the competition this year. It was tested with a wide range of randomly generated obstacles, including ones that overlap. During simulated testing, our obstacle avoidance system was tested against 147 obstacles, of which it avoided all but one. During outdoor flight tests, all 62 obstacles tested against were avoided. In order to verify that the Sony A5100 camera performed as expected, we started by doing a series of ground tests before taking it into the air. The initial test was to take images at a distance close to the flight altitude in order to test the image quality. This allowed us to see how easily targets could be made out compared to our predictions. Before being flown on the vehicle, the camera interface with the onboard computer was tested to ensure that the autonomous triggering of the camera and downloading of images worked as expected. After verifying that the flight performance of our vehicle was still good with the weight of the camera was then flown and used to capture images during mission tests. Our imaging system takes photos at a resolution of 6,000 by 4,000 pixels. After running tests on the imaging system, we determined that a ground sampling distance of 1 cm per pixel at an altitude of 165 feet was enough to detect all the characteristics of the objects which have the minimum character width of 1 inch. This quality corresponds to the smallest objects having a resolution of approximately 300 by 300 pixels. The UCAV team took several steps to ensure the best image quality. First, the camera is mounted on a 2-axis gimbal that keeps the camera pointed perpendicular to the ground. In addition, the settings on the camera were tested and adjusted until we reliably got clear images. To reduce motion blur, the search area is flown at slower speeds than the rest of the mission. Taking all of these steps is essential in order to give the detection and classification algorithms the best chance of correctly identifying targets. Autonomous detection and classification are handled through 2 processes. You only look once, which is used for object detection, and an array of standard convolutional neural networks for classification. The detection and classification algorithms have undergone a significant amount of testing. Throughout development, the neural networks have been tested with a wide range of generated images, which are designed to imitate flight test images as closely as possible. Although the algorithms are good at identifying generated images, they haven't performed quite as well on real images. As more real data becomes available and the neural networks get better training, we expect to see marked improvement in the characteristics matching performance. Localization testing was accomplished during full mission tests. The targets were geolocated manually with a phone GPS when they were placed, and then the locations were compared with what the localization algorithms calculated. The number of objects the localization algorithms were tested against was 10, and the average localization error was 15.2 feet. The airdrop has been tested successfully during several ground tests. No airdrop attempts have been made in flight at this point. The UCAV team performed full mission tests in a close approximation of how they would be done at the competition. The start of our mission testing included setting up the ground station, which has all the different required components for the competition. Part of the setup involves getting the 3 ground station computers up and running and connecting to a simulated interop server. Mock missions were planned, and then the mission data was downloaded from the interop server to the ground station computer. Once the mock missions are downloaded and the vehicle is set up and ready to go, we execute the mission. First, waypoints are flown, and then the vehicle goes to the airdrop location to release the payload. The vehicle is then routed to fly through the search area, taking pictures and uploading the detected targets to the simulated interop server. The mission tests that the UCAV team conducted are comprehensive enough that we are confident in our ability to accomplish our goals on competition day. The mock missions have tested the full system integration, ensuring that the hardware and software components work seamlessly together. Full mission testing has shown a few issues that need improvement before the competition. Our antenna tracking system lost connection during one of our flights, and we were unable to reconnect. Although this issue doesn't affect the safe operation of our vehicle, building in redundancies, including saving pictures to multiple locations and ensuring connection can be re-established, is an important step that is being taken before the competition. In addition, we have had a couple of unexpected motor failures, one of which resulted in substantial damage to our vehicle. In response to these failures, we have been forced to switch to motors that are proven to be reliable, though they don't have the same level of efficiency as the old ones. As of May 14th, the UCAV team has completed 8 full mission tests, with an average score of 64.95%. Currently, autonomous flight and obstacle avoidance are contributing the most points to the mission scores. With each mission test, we have included more components into our mission, and our mission scores have steadily improved. As we begin to implement the airdrop task into our mission tests, and continue to improve the ODLC algorithms, we anticipate that our mission test scores will continue to improve significantly. Based on our performance so far, we expect to score an 81.7% on competition day. With only a month until the competition, the UCAV team is working hard to optimize their system through more mission testing and continuous improvements. We are confident that on competition day, we will successfully complete all the mission goals that we attempt.